Okay, so from here we're going to take a kind of a slight detour from landing gear, but it's very methodical. We have to really understand hydraulics and how hydraulics works in order to really understand how a heavy commercial aircraft employs brakes. Now, the brakes in your car and the brakes in small GA airplanes are on their own independent system. There's a master cylinder, a slave cylinder, piston that then squeezes a brake pad up against a rotor, and all there's to it. Now, a heavy commercial aircraft works the same way, but that master cylinder slave cylinder component is integrated into the greater hydraulic architecture of the aircraft itself. So in order to truly understand those, we really need to have a fundamental understanding of hydraulics, and that's why we've saved it to this far in the course to employ it. So that way, once we understand hydraulics and hydraulic systems, then just applying them to the brakes is relatively simple. And then this will also set the stage for our assembly and rigging, because later on we're going to talk about flight controls and how hydraulics employs there. So let's start talking about hydraulic components and fluids, and kind of build a base so that way we understand where we're going. Okay, so the first component that we really need to talk about is one that's not unique at all. It's ubiquitous. It is going to be found on every single hydraulic system that you ever come across, bar none. At least none that I've ever come across. I've never not seen a hydraulic reservoir. Now, even your car brake system has a brake fluid reservoir. Effectively, that's just another hydraulic reservoir. Now, those systems and many systems on especially small GA aircraft are non-pressurized, just like this diagram right here. Now, there's two types of reservoirs. They're pressurized and non-pressurized. We're going to talk about the non-pressurized ones first because they're just a little bit simpler. All right, now construction of them. Let's talk about like why they're even there. They provide a adequate supply of fluid to the system. So in other words, this is you're going to have your hydraulic system charged and primed, so there's fluid in all the lines and the inside the pumps, everywhere it needs to be, actuators, you name it. And then there's going to be some that is left over, and that's going to go up into the reservoir. Now, what ends up happening is as we'll see here in a minute, that hydraulic fluid is going to cycle through the system. There's a bunch of reasons for that. It could be like cooling, cleanliness, you name it. But either way, there's going to be more hydraulic fluid than there is room in the actual lines, and that's what the reservoir does. Now, a non-pressurized reservoir is usually vented, so that way the hydraulic fluid can be pumped up into the reservoir and then sucked back down back into a pressurized system. The OH-58 was this way, and it vented to the atmosphere. So you didn't really have to worry so much about ever really bleeding the system. It would bleed itself because the vent was actually at the highest point in the system. So air always wants to go up and like float up, in the hydraulic fluid. And so eventually it would just work its way out. All you really had to do is just work the controls, and it would basically bleed itself. Whereas opposed to a pressurized system, you'd have to put pressure onto it and then let the air out and then close it really quick and then keep putting pressure, and you keep doing that over and over and over again. That's what bleeding the brakes is, and we're going to talk about that a little bit more as we get into this. But that's the advantage of a non-pressurized system. Now, a couple of things that we need to kind of point out here is that there's baffles and fins that are incorporated into the reservoir to keep the fluid within the reservoir from having random movement, like vortexing, swirling, surging, sloshing around, things like that. This is true of also fuel cells. You have a big reservoir. And so imagine kind of like a big bathtub. Now, a bathtub doesn't have any baffles in it because you got to lay down in it and take a bath. But if all of a sudden, say that bathtub was in an RV, and that RV hit a bump, all that fluid would go sloshing around. Well, think about just weight and balance wise. If there's a lot of fluid that goes from one end, you've changed the CG of that component, and therefore the CG of the apparatus that's holding that component. In this case, like a fuel cell, all that fuel rushes to one side and causes the plane to behave a certain way, and then action reaction, and wants to rush back, maybe to a lesser degree, but it still causes the CG to shift again. All the while, it becomes really, really difficult to control. Hydraulic fluid is no different, especially whenever you start talking about like really, really big aircraft that have a lot of hydraulic fluid in it. You want to make sure that that fluid can't just slosh and swirl and vortex and go all over the place. So you put fins and baffles in there. Now the baffles are really simple. They're just basically little metal structures that just disrupt the flow. If it all starts going one way, it hits a wall and then has to go through these very small ports. And so by the time that hydraulic fluid starts to bypass that baffle, the airplane's basically corrected itself, and so the effect you get is a very stagnant status, or very stagnant hydraulic fluid that can't just move around all over the place, and so that's why they are there. Now, other things to look at, we've talked about the vent line. There's always a filler cap that is going to get just basically be an open place for you to put fluid in there. On non-pressurized systems, they're just basically just a cap like you would on like a antifreeze on a car or your brake fluid or whatever. You just open the cap, pour the hydraulic fluid in, and then close it. Then there's always going to be some way to know how much fluid's in there, and it's usually going to be a sight glass. Like on this one, you can see on the right hand side. These can look in a variety of different ways. They can be a long graded sight cap, like you'd see on our IDG on the JT9s. They'll have like this long, like kind of rectangular sight glass that says like, hey, look, here's like a gallon, here's 2 gallons, here's 3 gallons, or whatever the unit of measure is. More often than not, they're actually just going to be a circular sight glass, and your goal is to make sure that the hydraulic fluid cuts that sight glass in half. It's like perfectly at kind of the 50% mark. Now that can change depending on the hydraulic system you're looking at, so you always want to make sure you know what the servicing requirements are as per the maintenance manual. They'll also usually be in some other documents as well on board the aircraft. You also want to make sure that the conditions are correct, because like I'll give you kind of a story. And this isn't a hydraulic system, it's a helicopter transmission, but it kind of serves the purpose. On the OH-58, you only wanted to service it whenever the transmission was cold, and that's because the transmission oil would expand whenever it got hot. Well, so if you were to say come in and say like, hey, look, the transmission fluid is like way too high, right? Because it was hot. Well, then you would then drain it all out, and then you'd come out the next day, and well, now it's like way too low because it got cold and then it contracted down. And so you always wanted to make sure that the helicopter was cold, and then the hydraulic or the transmission fluid was at the correct mark, because then you know that is the right amount that is designed for that system. You never wanted to service it hot, because you could over service it as well, which isn't necessarily what you wanted to do. So that's something to keep in mind. Now, most of the time your hydraulic fluid is by nature not going to expand or contract that much, but you never know what you're going to end up working on and what the properties of that particular fluid is. 5606 Skydraw, that kind of thing, they're not going to expand or contract that much, and so you don't have those concerns. But like I said, you never know where you're going to go. So that's a good rule of thumb. Any type of servicing, you always want to make sure that the conditions are correct for the servicing to happen, so that way you don't make any kind of mistakes. But yeah, so like that is what a sight glass is. Now the other kind of connections that you see on this thing is that you have a return line, and then you'll have an emergency line, and then you have a main systems pump line. Let's go through those. So the main systems pump is pretty simple. Like that's the feeder that's going to go into the hydraulic pump that's going to pressurize the lines and send it all out. Now the return is where the hydraulic fluid is going to re-enter the reservoir. So it's going to come back in. So it's always going to be flowing. And the reason why we do that, the big reason why we do that, is make sure that we have a way to catch any trash that's in the line. Now, technically, you could probably charge the system one time and then close it off, and if it maintained that level of pressure, it would work and do what you wanted to do based on the way hydraulic fluid transmits pressure. Which we'll get to that here in just a little bit. But if we pressurize it, then we let it move around, it becomes a self-cleaning, self-purging. It does all kinds of really good things if it moves that way. So that's what the return line is for. So you have a main system line that goes out, a return system line that comes back. Now, there's also a connection here for an emergency systems pump. Now, this is going to vary widely from aircraft to aircraft. If you think of like a 737 is going to have three different hydraulic systems that will integrate. If I remember right, it's either two or three. Airbus absolutely has three. They have three different colors, like a red, blue, green hydraulic systems. They're all intertwined to each other, and then you have like standby systems as well, and then other standby apparatuses that could be deployed, like the RAT that could pressurize the hydraulic fluid. All that, while all of it's fundamentally very simple, it becomes very complex whenever you start integrating all these different things together. But the kind of the rule of thumb is that like if there is a need for hydraulics on the aircraft, there's almost always going to be some sort of emergency or backup of some variety. So if you look at like the Aztec that's on our hangar floor right now, their landing gear system will deploy based on just hydraulic pressure, just like it would like a 737 or whatever. But if it fails, there's a hand pump, so you can hand pressurize the hydraulic fluid and get everything to work by simply like just hand pumping the airplane. That is a type of emergency hydraulic fluid that could be employed, or emergency hydraulic system that could be employed. So just know that is thing. But anyway, so that's a non-pressurized system. The main thing to keep in mind there is that it's vented to the atmosphere, and it's not pressurized. Usually, it's always going to be at the highest point in the entire system to allow the air to escape, which has the advantage of being self-purging. Okay, so there's two kind of subtypes of pressurized reservoirs. We're going to talk about the more unique one first, and then we'll talk about the more common one that you'll actually find on like heavy commercial aircraft. The first one is going to be a fluid pressurized reservoir. Now, some aircraft hydraulic system reservoirs are pressurized by the hydraulic system pressure itself. The regulated hydraulic pump output pressure is applied to a movable piston inside a cylindrical reservoir. Now, this piston is then attached and moves a larger piston against the reservoir fluid. The reduced force of the small piston when applied by the larger piston is adequate to provide head pressure for high altitude operation. The small piston protrudes out of the body of the reservoir, and the amount exposed is used as the reservoir fluid quantity. Now, this graphic illustrates the concept behind the fluid pressurized hydraulic reservoir. Now, there's got five parts: the pump suction port that comes out, the return pressurizing port, the overboard drain, and then the bleed port. Now, fluid supplied by a pump through the pump suction port, and fluid then returns to the reservoir from the system through the return port. Pressure from the pump enters the pressurizing cylinder at the top of the reservoir through the pressurizing port. The overboard drain drains the reservoir when necessary while performing maintenance. The bleed port is then used as an aid to servicing the reservoir. Now, the more common pressurized reservoir that you're going to find is going to look something like this. Now, the reason why they get pressurized is because, like, if you look at a 737, the reservoirs are going to be inside of the wheel well. Well, the wheel wells aren't pressurized on a 37, so that means that whenever you get up to altitude, you need some sort of pressurization on the fluid itself or on the reservoir itself in order for it to work. So they use engine bleed air to pressurize that reservoir. The reservoirs are typically cylindrical in shape. So this one's kind of like a little fat cylinder, and that's what they will look like. And I'll put a picture up of one here in a minute. And then they have a couple of parts. So first off, they have a pressure relief valve that prevents over pressurization. So kind of like your hot water heater has a little poppet that will pop off if the hot water pressure gets too high. The reason being is that you don't want to over pressurize basically what would become a pipe bomb inside of your landing gear. So if it like starts to get too much, that relief valve will pop and let the pressure go out. Then you'll have to deal with not having any hydraulic pressure as opposed to literally like blowing the fuselage in half. Now, on a 37, you will have cables. You'll still be able to fly the airplane. On other aircraft, you'll have a little bit more of a challenge because then you'll have all your hydraulic fluid will leave. It doesn't quite work that way, but that's generally kind of the problem set that's there. So the pressure relief valve is really important. Then obviously you have your sight glasses. That's going to get checked every time the aircraft lands. The maintenance can come on there and look at it and be like, hey, look, it's good to go. Send it back. It works just like we talked about. There's a reservoir sample valve. Now, we haven't got to fuel systems yet, but this is something that's really common on fuel, is that you'll sump the system like every single time that the aircraft either goes to fly the first part of the day or gets fuel and or. So the sump valve on a hydraulic system works, much the same way, that you'll be able to go up there, pull a sample out, make sure that all the trash is out of it, and that there's no like metal flakes in it or anything that could potentially cause a system failure. All right, then there's a temperature transducer that's going to transmit the temperature up to the cockpit and let you know what your hydraulic temperature is at. That is going to be indicative of like component failure. If you think if you have like a pump that's going bad, it's going to probably increase in temperature, and it's going to impart that onto the hydraulic fluid temperature, and let you know that, hey, look, we have a problem down on board. Simultaneously, you also have a fuel or a hydraulic fluid quantity transducer that will also go up to your hydraulic panel, let you know how much is actually in the system. Now, that doesn't replace the sight glass, because there's always the possibility of an instrumentation error between the transducer and the cockpit. It could be any number of things. It could be corrosion on the connectors, could be a broken wire, it could be just a bad transducer, any type of thing that could cause some sort of stray voltage, some sort of deviation in the transmission of that information. And so nothing's going to really surpass literally putting human eyeballs on it, but you can't do that in flight. So you get to have something to let you know, hey, this is what our hydraulic quantity is at. So that way, if you have the quantity and you have the temperature, you have a pretty good idea of the health of the system at any one point. It's just kind of like your blood pressure and in your temperature itself. Like if you know that, like, hey, look, this person's got blood pressure that's just falling off or whatever, that's probably a good indication that, hey, look, they are they're hemorrhaging, they're bleeding out. It's the and they're going to die if we don't do something about it. Same thing if there's an over, you start running high blood pressure, you have a good chance of blowing your aorta out. So we need to do something about that as well. So anyway, so that's how you can kind of check the health of the hydraulic system. Okay, so the next kind of ubiquitous component that you're going to find in all hydraulic systems of any type is going to be some sort of filtration. Now, typically in hydraulic systems, you have micron filters. All right, so a typical micron filter assembly is employed, and the reason being is that little shards of debris inside of a hydraulic system can cause serious problems. And so, as a kind of industry, aviation has just set a very high standard for filtration of its hydraulic fluid, and honestly, many of the other types of fluids out there. But let's talk about what a micron is. So, 2,000 or 25,400 microns is the equivalent of 1 inch. Now, for perspective, your hair in your head is about 100 microns across. All right. Now, most of your hydraulic filters out there are going to be like 10 micron filters. There's some bigger that are like 40 microns, and there's some that are like, just really, really ridiculously small, like 5 micron across. Now, when it says microns and you're looking at, what are they measuring, they're talking about the holes in the filter itself that catches the debris. So in order to go through a 10 micron filter, you have to have a particle that's smaller than 1/10 of a human hair to get through that filter. So even if it does manage to exist in the hydraulic fluid and it manages to get through there, it's likely going to be so small that it's not going to be consequential to anything inside of the hydraulic system. It's not going to be big enough to really derail some sort of actuator, and it's not going to burn up a pump or anything else like that. unless you get a whole bunch of them. But they'll start to pile up on the filter itself, and you'll end up having to you'll get a filter bypass warning and have to deal with that. So that long story short is that whenever we start talking about like hydraulic filters, know that they are filtering to a very high degree of fidelity of the and ensuring the quality of that hydraulic fluid in that system. Okay, when it comes to servicing your filters, there's going to be two basic actions you're going to take. There are reusable filters that you can clean and your maintenance manual will tell you how to go about cleaning them. Sometimes you take them, you flush them, or sometimes you take them, you blow them out. A lot of times you're going to take those filters out and you're just going to throw them in the trash and put new filters in. It becomes pretty simple. And this is actually a pretty regular, reoccurring thing that will end up happening. Now, on some aircraft, you have bypass valves. So let's look at the schematic of a thermal bypass valve, but there's other types as well. Okay, now what these will do is that you'll have like a little indicator button on the filter housing assembly. Oftentimes it's at the very top. This one is kind of arranged in a little bit of a different way, but typically you have a bowl that's going to be vertical, and then on the very top will be this little bitty red button that'll pop up. That button pops up under a couple of certain conditions, but effectively means that there's no fluid flowing through the filter because the filter is clogged. And so typically what happens there is that there's something that's gone bad. Almost every single time I think I've ever worked as the hydraulic pump starts to fall apart on the inside. It puts a bunch of like trash into the stream of hydraulic fluid that starts to be caught inside of the filter. The filter's pressure gets too high, and then it causes the button to pop. Now, once that button's popped, one of two things could happen. Either A, you could get an indication in the cockpit that says like, "Hey, look, this filter has been bypassed," and whenever the plane lands, the helicopter lands, they're going to contact maintenance to go and see what happens. You're going to have to take that filter out, replace it. Usually, we'll do a flush of the system to get anything that could potentially be out of there, out, or any kind of trash is in there out, and then recharge it, do a quick maintenance operational check or MOC. You're going to hear me say MOCs a lot because we're going to start talking about systems. You're going to MOC the system, and then if everything passes per whatever AMM task you're working to, you'll return to service, and it's no big deal. Now, there's another scenario where it doesn't give an indication in the cockpit, and that is meant to be caught on a walk around, either post flight or your maintenance daily checks or whatever the maintenance system is that's being employed in that particular operation. But these are things that are good to know because whenever you're doing your walk around, you should always put your hand on it and make sure that it's not popped up. Now, the reason why I say do that, it's not because they only come up halfway or anything else like that. It's because if you're physically in the habit of finding this thing, putting your hand on it, there's a very low chance that you're ever going to miss it. So whenever you're doing post flights or you're doing dailies or something like that, it's really a good practice, a good habit to get in, and it's a good professional way to go about it. Is always put your hand on there, and bonus points if you take a shop towel and wipe everything off. Just cleanliness generally leads to being able to maintain the aircraft to a high degree of professionalism. And then on top of that, if there's any kind of like hydraulic fluid leaking out of that system anywhere, you're going to pick it up on that shop towel really fast, and then know that there's something you either need to watch or need to address right then and there. But that's how these things work. Now, this has a thermal lockout that could potentially happen if it's cold. It won't let the button pop, and won't let the filter get bypassed. If it's hot, it will. So know that there's going to be a level of complexity to systems like this. I've never quite seen this one that I'm aware of. And anyways, yeah. So that is a filter bypass valve. Okay, so let's talk about different types of pumps that you can find on an aircraft hydraulic system, and we'll get into the role the pumps play here in just a minute, and then whenever we actually start talking about the hydraulic system itself, we'll talk about like the all-encompassing why do we have hydraulic pumps. This one is a hand pump from a Cessna 210. So if the engine and electrical hydraulic pump fails, you can pump the gear down. You can actually use just a much like you would like raise a car with a bottle jack. This is very similar kind of operation that you'd be able to pump the landing gear down until they lock into place. You notice that the long black cylinder with the red ball on the end is a handle that's going to be in the cockpit. You're going to grab it. It's going to be mounted with those two mounting bolts that you see on the cylinder right there. And as you ratchet it up, or down, it's going to push hydraulic fluid into the system under pressure, and then whenever you come back down with there's a check valve to keep the hydraulic pressure from coming back with you. It's going to be locked into place, and then you're going to have a suction that pulls from the reservoir, and then you pressurize it again as it goes back up. The simple math of the cylinder that the hand pump is moving, and then the aperture in which the fluid is being forced into, it will result in a certain amount of pressure that's been formed out. The main thing that you have to bring to the table is just calories. You're going to end up having to hand pump that thing for a hot minute to get the landing gear to come down. Now these are often used as backups. So like we have one on the Aztec that you'll pump whenever we do gear swings. Yeah, so that just know that is a way to increase the hydraulic pressure in a system. There are other types of hand pumps that you'll see on some of the heavy commercial aircraft as backups for ground use, but you're not going to see anybody hand pumping down 737's gear by any stretch of the imagination. Okay, so the kind of primary method of getting hydraulic pressure into the system is going to be an engine-driven pump, like you're seeing here. Basically, as the engine turns, it's going to turn an accessory or an accessory gearbox, and then the hydraulic pump is going to be attached to that engine accessory gearbox. And as it turns, it's going to provide hydraulic pressure for everything else. Now, this is kind of the I guess preferred method. There is another method that's typically used for ground operations and for emergency situations. Okay, and that method is a electrical pump. Notice that you have that big cannon plug there with those heavy wires. That's going to be your electrical supply, and this is just an electrical pump like anything else, just like a sump pump in your house or anywhere else that you'll see. This is definitely the way that things are going. You're going to see more and more of these electrical type pumps and more and more aircraft. To the point where the 787 even uses an all-electric hydraulic system that's in there. It's simply because they're more reliable, they're modular, and easier to maintain. An electrical pump, essentially, all it really does is you turn a switch on, it starts to pressurize the hydraulic fluid, and you're off to the races with that. Very common to be used as a backup. Slowly becoming more and more of the. Okay, all pumps basically fall into one of two categories. They're either a constant displacement or a variable displacement. Constant displacement basically means that no matter how fast the pump turns, it will produce so much pressure, so much flow. A variable displacement will change the pressure based on how fast the pump turns. So, like, the faster it turns, more pressure, more flow. Slower pump turns, less pressure, less flow. Now, beyond that, there are different different ways these pumps operate. Now, what you have in front of you is a gear type power pump. The way that this works is that the clearance between the teeth mesh together, and they basically grab little bits of hydraulic fluid at a high pressure. Then as the teeth goes around the outlet port, it basically shoves that pressure out into the line. So you'll have a driven sprocket that will grab another similar type sprocket on the other side, and that they will come together. Now these these teeth on these different gears, they are very, very, very close in tolerance. But there's enough room in there for them to grab the hydraulic fluid and then pressurize it with just like them squeezing the fluid. And then as it goes around, it basically releases it. Off it goes into the outlet. Now these are pretty common. You'll see them around. But there's just one type of hydraulic pumps out there. Now, keep in mind, a lot of these different types of hydraulic pumps we're going to get into, at the end of the day, you as the mechanic, you're just going to remove and replace whenever they go bad. Where this is going to help you is with troubleshooting. If you say like, hey, look, I see that the hydraulic pressure is just not what it should be. Let's say it's supposed to be at 1,000 psi and it's at 950, and I just cannot figure out why. And last week it was at 975. But like, hey, look, the pump is still good as long as it's producing 900. Well, that tells me that the pump is starting to go out, and the reason why the pump is starting to go out is because likelihood is that those little sprockets are starting to wear down, and so that now there's like more and more of a gap between them to hold hydraulic fluid. And if there's a bigger gap, there's probably less pressure, and then you can kind of extrapolate that out. That's why like we kind of go into these different classifications of pumps. So that way you can kind of think through the problem rather than just doing what we call shotgunning parts, just change one thing or the other. But anyways, so that is a gear type pump, and next we're going to go to the gerator pump. Okay, so a gerotor pump is fairly simple. You're going to have a gear that works that turns around on the inside, and as it turns, it's going to grab little bits of fluid, and it's going to create a pressure cavity between the main drive gear and then the housing that sits into it. As the drive gear rolls around, it's going to then pass by an inlet and then push the fluid downstream. And that's going to be pressurized, and off it goes. Now, where this differs from most other pumps, like in our drive gear pump that we looked at, there's two gears that do this together. Effectively, it's like double what we have here. In a typical pump, you'll have a crescent that instead of those two gears passing by the inlet, one gear will create a pressure cavity, shove it behind a crescent. That crescent will then travel around to the inlet and then release that pressure cavity into the inlet. And it's doing it really, really fast. So technically, there's like a rhythmic release of pressurized fluid, but it's happening so fast it's like basically like one solid stream to unless I guess you have a high-speed camera, you can slow it way down. Anyways, a gerator pump, you have a fixed housing, and then you have that single sprocket that goes around and does all these things. Now, the reason why that we want to know this is so that way we can troubleshoot just like we did with the drive gear. It's not to just fill your head with useless knowledge. It's actually there for troubleshooting purposes. So if you understand that it's a gerotor type pump, or it's a gear driven pump, or it's a centrifugal pump, or whatever, you can kind of understand how it works and why it works, and then and extrapolate the effects that it's going to have on the greater system. Okay, another type of pump is a piston pump. What you're looking at right now is an axial inline piston pump that uses a swash plate and a series of pistons to move hydraulic fluid from the inlet port to the outlet port. Whenever the pistons pass the inlet port, they are all the way down, bottomed out of the swash plate. That chasm creates a vacuum which pulls hydraulic fluid in, and as it goes around the swash plate, it starts to pressurize that hydraulic fluid until it gets to the outlet pump, and then it pushes it out into the outlet port. That is fairly common. You'll actually see these out in the fleet. Okay, here's another type of pump that you could come across. It's a bent housing piston pump. It basically is same kind of configuration with the pistons and the housing. The difference is that it's offset at an angle to make it fit in a certain area. What's really going to be fundamentally different from this one, though, is that the drive and in the inlet and outlet port are opposed from one another. Whereas before you would meet up with a drive on one side, and often your inlet and outlet ports would be part of that. So you would just simply just attach the hydraulic pump to the housing. This one, it's the drive's on one side. It's going to go through a universal joint to get the angle that you want, and the inlet and outlet ports are going to be on the back side of that pump, so diametrically opposed to the drive side. And as the it works the exact same way as the pistons spin around. They occupy different spots in the housing, and thus moving the hydraulic fluid from a negative space to a more positive space, and eventually to the outlet port. Okay, so now let's talk about the actual hydraulic fluid itself. Before we get into the different types of hydraulic fluids, let's talk about like four attributes of hydraulic fluid, or really kind of any fluid, but specifically they become very, very important in the worlds or in the context of hydraulic fluid. So first off is viscosity. So as defined, viscosity is just the internal resistance to flow. Now viscosity is pretty easy. If you think about water as being a viscosity level 0, it's just water. It'll flow and do all kinds of stuff. But then you think about like pancake syrup. Syrup pours out really, really, really slow, and it gunks up, and it just really binds together, and it's really thick. That's a viscosity level 2. It's a lot more viscous than say just water is. If you were gonna make some gravy, and like the gravy's all watery and runny, it's a low viscosity. And you wanted to thicken it up, you would put a bunch of flour or thickening stuff in. I can't remember what my wife puts in the gravy, but essentially like you put stuff in there to cause it to thicken up, to have more adhesion to itself, and so it will have a higher resistance to flow. It'll drip out slower if it's highly viscous. Now. The next one is chemical stability. That's the ability to resist oxidation and deterioration for long periods. So that's a fancy way to say, does it break down over time, yes or no? Or does it break down with a little bit of electricity or a little bit of heat added to it? How resilient is it to change? So like water is basically super duper stable. It takes a lot of energy to get water to break down, and the only way that water really breaks down is through a process called electrolysis, where they run electricity through there and they separate the hydrogen from the oxygen. And then if those two off gases come in contact with each other again, they'll just reform into water. It's very, very, very stable. Some chemicals are not stable. Like if you were to set hydraulic fluid out. Hydraulic fluid's really stable. It'll be there for a long time. But let's say if you were to set fuel out, fuel's less stable than hydraulic fluid. So the fuel will eventually break down, and you'll even see the additives start to separate in it over a long period of time. And there's other chemicals as well that will break down over time. So that's chemical stability. Next is flash point. So flash point is the temperature at which a liquid gives off vapor in sufficient quantities to ignite momentarily or flash when the flame is applied. Now, flash point is a very common data point for most liquids that you'll come across. You'll see it very clearly displayed on the sides of cans, on charts, things like that. And the reason being is that everybody needs to know what chemicals are flammable and which ones are not. This chart here will kind of show you what flash points are considered flammable and which ones are not. Reason being is that it's very easy to hit 73 degrees. I mean, if that's basically room temperature. So at room temperatures, that fluid will off gas flammable liquids, and it could actually spark and catch on fire. And then even up to 140 degrees, you're kind of cat 3, cat 4 flammable liquid. If you take a can and say leave it out in the sun, even in the middle of winter, it could get up to one of those temperature thresholds. 140 degrees in the middle of a desert in Iraq, I'll tell you, is very easy to do. You put something that's like a Cat 3 flammable liquid in a can, and then set it out in that sun. It very well may spontaneously combust. So these are things that you need to know about certain liquids. Now, when it comes to hydraulic fluid, and we'll get into the different types of hydraulic fluid here in a minute. They're all going to have different flash points, but they're all very, very high because they wouldn't be very good if they had low flash points and you started running it through a hydraulic system that inherently gets really hot. But that's what flash point is. Okay, so fire point is the last attribute that we need to talk about. That's fire point is the temperature at which a substance gives off vapor in sufficient quantity to ignite and continue to burn when exposed to spark or flame. Now, flash point is just whenever it gives off just enough to cause a flash, and that's usually considered that's the point where it could potentially burn, but it's actually kind of wrong. Fire point is the point in which the chemical has gotten hot enough to just produce a continuous amount of flammable gases that can flash and continue to burn, without any sort of stop. Now the thing is that the moment that you get a flash and something were to flash, that heat's going to come up, and you're going to bring that liquid even higher up to the fire point. And the flash point and the fire point usually aren't that far apart, so it's kind of it's a technicality to separate flash point and fire point, because usually if it's flashing, it's not too far along, it's going to be at the fire point as well. The point being is that there are two separate points in the temperature progression of a fluid. So now let's talk about the different types of hydraulic fluid. Okay, so the oldest and probably one of the most common hydraulic fluids out there is Mill H5606, or commonly referred to as 5606. Now, the picture you see up on the screen right now is a Royco 756. It's just Royco's product that is 5606. The 5606 is an industry standard number that Royco has made their product 756 up to. But you'll never hear anybody say, "Give me some 756" or whatever, unless they're just, I guess, really into hydraulic fluids. Most of the time, people will say 5606, and they don't really care so much what brand it is or anything else like that. It's processed from petroleum, so it's an oil byproduct that gets made. Thus, the classification, it's a mineral type of hydraulic fluid. Now, these have been around since the 40s. It's probably the oldest. It's the most widespread. Most your general aviation aircraft, your smaller, like your single engine piston aircraft, are going to use 5606. If not in their hydraulic systems, but definitely in their braking system. So, like my Piper Cherokee takes 5606 in its brake system, which is effectively a hydraulic system. But yeah, so that is one of the most common that are out there. So if you get into GA, you get into a lot of helicopter stuff. That's what they're going to end up using. Okay, once you're through with the mineral-based fluids, the polyethylene-based fluids to kind of take their place. Now, specifically, 832-82 took 5606's place in a lot of different aircraft. Now, you'll still see 5606 that's out there, but 8032-82 is basically the same type of hydraulic fluid, just with an eye towards flammability. So you notice that really, big letters on this can, it says fire resistant. 8032 basically raised the flash point significantly of 5606 to cut down on the possibility that it could catch on fire. Now, back in the day, there was a lot of aircraft fires, and then it was spawned from overheated hydraulic fluid gets leaked out. It off gases. There's some sort of spark or something that catches on fire. Boom! The whole aircraft goes up in flames. So people wanted to come up with a way to mitigate that, obviously. And 8032-82 was one of the steps for it. But you'll run into this out there in those hydraulic systems. Okay, and finally, phosphate ester-based fluid, or commonly referred to as Skydrawl in heavy commercial aviation. This is the most common hydraulic fluid that you will come across if you end up working on heavy metal aircraft. I will tell you, it will burn your skin, it will burn your eyes. You don't want to get this stuff on you if you can help it. But a lot of times, especially if you're working in the wheel well of a 737, this stuff is everywhere, and it's going to get on you. Now, they come in two different types, and I'm just going to read you a paragraph out of 8083 because it breaks it down pretty well, and there's a lot to it. So today, Type 4 and Type 5 fluids are used. The two distinct classes of Type 4 fluids exist based on their density. Class 1 fluids are low density, and Class 2 fluids are standard density. The Class 1 fluids provide weight savings advantages versus Class 2s, which I thought was really cool that they actually thought about how to reduce the weight of the fluid. In addition to the Type 4 fluids that are currently in use, Type 5 fluids are being developed in response to industry demands for more thermally stable fluid at higher operating temperatures. Type 5 fluids will be more resistant to hydrolytic and oxidative degradation at high temperatures than at the Type 4 fluids. So, Skydraw, by far, probably the most common hydraulic fluid that you're going to come across. In your more simple airplanes, they generally will use push-pull tubes and cable systems. You won't see a whole lot of hydraulics. Once you start getting into the jets, that's when you'll start to see a lot more hydraulic implementation, simply because of the way, the amount of weight that that the flight controls need to be able to deflect the air to cause a reaction in the airplane. So hydraulics gives you a way to put a little bit of effort in, but get a lot of output. And so as you start to progress up in the complexity of aircraft, you get more and more hydraulics, and it doesn't take very long to outgrow 5606 and 832, and you start getting into all the ester-based fluids like Skydraw. There's other brands that are out there. Skydraw is just a brand that's out there, but it's probably the most prolific and most common brand. Another one that you may run into is Hijet. I've never actually seen it used. I think I've always serviced with Skydraw. Okay, so a couple other notes on hydraulic fluids that you can't mix and match. The chemical basis of all three of these types uh, of hydraulic fluids are very different from one another, and that means that the equipment that they're going to be going through, the seals, the hoses, all of that is going to be kind of tailored to that particular hydraulic fluid, and so you don't ever want to mix and match them. And on top of that, they don't necessarily work together very well. So one of the things that you're going to continuously do is contamination checks. Now this can look very different on different aircraft and different maintenance programs, but a sample system like you see here, where the guy's taking a hydraulic fluid and put it in a jar and he's about to ship it off to a lab, is very common. And it's also, you'll see these happen with engine oil whenever we get to that in power plant. But anyways, like what they're going to do is they're going to check and make sure that it's the right hydraulic fluid, that it doesn't have any contaminants. Now contaminants kind of break down into two families. One are abrasives, so this is just like chips and dirt and junk in there that just erode like the pumps and the equipment that the hydraulic fluid comes in contact with, and then non-abrasives. And I've seen this actually probably more often than abrasives, that you'll have like some sort of little bits of like, it's almost like black flaky stuff that'll develop inside of that hydraulic fluid, and that's what filters are for, to catch those types of things and filter them out. And then you'll also do draining services on a pretty regular basis. But I don't want to get too far into that because we have filters are kind of their own class. But I will talk about like some drain and flushes. So typically, whenever you have any sort of contamination issue, or any sort of honestly any sort of maintenance issue with any sort of fluid system, one of the first things you're going to do is drain all the fluid out. Then you're going to take the filters out, put a new filter in, and then resurface it. And you may even drain it all out and then flush it with the right type of fluid multiple times, and then you finally service it for the last time. If you get into helicopters, transmission drain and service is something that happens on a regular basis. If you get a positive hit on a chip detector, a drain and service is like one of the first things you're going to do. Is going to try to get all the metal out before you end up replacing any big components. And so that's a task that you can pretty well bet that you're doing. And so being able to handle these fluids without getting it all over you is a key skill for you to develop, because you don't want to have all, especially Skydraw. You absolutely do not want that on your skin if you can help it.